Welcome to the second software meetup of ProDive Technologies. In this video, Usman and I will tell you more about data analysis in the manufacturing domain. My name is Timo and I will tell you something about my coordination projects which I performed here in the data analysis team at ProDive, which is about scrap prediction and defect analysis from process data. First, I will tell you something about the use case. The use case we took for the project is about the air quality sensor, which is produced in-house here at ProDive Technologies. It's quite a complex product. It has very high accuracies, and therefore it's quite difficult to manufacture. This also has as a result that the root cause analysis is quite difficult because there are quite some high accuracy processes involved, and therefore investigation by hand is quite time consuming. It's produced at the automated assembly line, which is also developed in-house here, which consists out of separate automation cells, which are placed sequentially after each other. The automation line consists of several processes, and a total of more than 700 parameters are stored for each individual product. The use case was also good because it had a high volume, which resulted in a lot of data which we could build models. You can see in the picture here that in the beginning of the data set the number of products was lower because it was still in the ramp-up phase of production, but in the end the manufacturing numbers increased quite significantly. The goal of the project, we had first some problems which we wanted to tackle, which were that there was quite some time-consuming defect analysis, because if you're gonna investigate all the separate parameters by hand, this is gonna take quite some time. Also, the data is stored in separate data sources. So if you want to combine, for instance, the process data with the product information, you have to look into several databases and combine this by hand. And we want to minimize the component scrap, because components are more and more scarce in these times. We want to minimize the waste from the products which are not successful in the manufacturing process. To solve this, we want to build a data framework in which multiple data sources are combined, and with this data we want to model. This model we want to predict scrap during the assembly process. So at each step of the process we want to determine if the product should continue or not. This model resulted in the picture below, in which we combined several data sources into a single framework. With the framework we want to obtain the control limits and eventually make a scrap prediction. First we used the data from a mesh system. This is an event-based system in which the production times are logged for each product. So the start times, the complete times, and also all failures for each product are logged. And this is combined with the data from the data collection. The data collection contains all data which are produced at the automation solutions, which contain information about the process itself. So for instance, at pick and place solutions, you store data about the position of a component, and at heat staking you, for instance, store the power or force with which a component is pressed. In the beginning we did some pre-processing, which is quite standard in machine learning practices, and we also got some additional features out of the model. Based on the mesh data we determined the process time and the time in queue to see if these features influenced the performance of the product. And also we determined the outliers, which are added also as additional features. On the right here you can see the division of the scrap labels. You can see that the classes are imbalanced, but there's also enough information to determine a good model, so we have enough information about both classes. This model resulted in a proposed framework, which is stated here below, in which at each step is individually modeled, and then the data is stored. So if we need to iterate certain steps, we don't have to rerun and extract the whole model anymore. The first modeling step was to build a performance probability model with which we want to assess the quality of the product. We did this by implementing an XGBoost model, which is a quite well-known model in machine learning practices, and is also fast performing and also suitable for unbalanced classes. It's for instance also used in detection of credit card fraud, and because of the similarities with our use case where we also want to detect the minority class of products which are non-conforming, we chose for this model. We've selected a model, implemented it for each individual workstation. So at each workstation there is a prediction made. So at each workstation we can determine if the product should continue with the process or not. These decisions are made from the process data from that single workstation, and out of the initial classification of the conformance we can also put out a probability of this classification. We use the chronological train test split data because we have seen that in the beginning of the data set there were quite some process changes, and therefore if we're going to shuffle data around, for instance for cross-fault validation, you're going to train your model with future known data when changes have occurred, and then your performance is actually better than it would be in real life. So therefore we decided to keep the data in the correct order and made a prediction at each week of the production process. Out of this initial model we got a heat map with all the false positives per week per workstation. The dark blue spots represent points where there were quite a lot of false positives for products which were actually good but were targeted as non-conforming. This is not what we want, as we want to predict scrap with a high precision. At the end of the line all products are tested, so if we miss any scraps during the prediction this is not a big deal because these are filtered out at the testing stage at the end. These failures were due to process irregularities. So if the process changed, for instance robot programs are changed or physical grippers are changed, the mean of a measurement value can change, and then the model assigns all these products as non-conforming. This is actually what the model should do, but as these are intended changes, this is not desired. To solve this we applied some class weighing which favored the non-scrap class more than the scrap class to reduce the number of false positives. This helped quite a lot, but it reduced a little bit the performance of the model. It did not fully erase all the cases with high positives, and therefore we decided to filter these out manually and later in real time implement a system which can keep track of the process irregularities which are performed intentionally. This gave us the following results. You can see that the precision is not as desired yet. There's still quite room for improvement, and this lower precision was due to the mentioned process irregularities, but also that we trained all individual models with a single training label. We had only the single training label available in which we say that the product is scrap or not, and we trained all individual models with this. But if for instance a deviation occurs halfway the process which leads to scrap, you also train the workstations before that with the wrong label. Also from the model we could obtain the feature which was most likely the cause of scrap. In the picture you can see that the top feature contributed most to the decision of the scrap, and therefore is assigned as the probable cause. This can help engineers in their investigation. So if they have a lot of scraps and these have similar root causes based on the model, they can start looking more targeted than that they have a whole assembly line with 700 parameters where they need to start looking. To improve the precision of the model, we suggested a second modeling step, which combines the probabilities out of the classification model from all workstations together. So actually decisions can be made on the results of multiple models. The first method we suggested for this is the cumulative exponentiated probabilities method. In here all probabilities are cumulative summed at each step of the process, but this gives issues as you have a lot of low probabilities. These can, if you sum them all up, exceed one high probability. So therefore they are exponentiated, so that the difference between low and high probabilities is larger. And then eventually, if they surpass a certain threshold, they are classified as scrap. In practice it looks like this, where first the probabilities are exponentiated, then summed, and then when they exceed a certain threshold, they are scrapped. The second method was a neural network method, which could learn on its own when the probability is high enough to determine if it should be scrapped, or to combine multiple workstations and determine which workstations in the assembly line are more important to determine if a product should be scrapped or not. And this looks like this for multiple workstations, where at each workstation the inputs from all the previous workstation is taken, and then a decision is put out. The following results were obtained. You can see that the precision of the SEP method is quite larger than the neural network method. The SEP method were quite good because we implemented a higher threshold for the classification. What's also interesting to see is that as the dataset grows, also the number of true positives grows. You can see that recall decreased from the XGBoost model, which only did the quality conformance. Because you have a more stricter model, then the recall of the amount of true positives is also lower. To determine if the model can actually deliver something, we need to take into account the cost. So here in the graph is plotted with the cumulative sum of all the component costs which are added during the production process. For instance, if we assign a scrap during the production process in the middle of the line, we have two cases. The first one is that we predicted it corrected, and then we save component cost from the components which are not placed afterwards. But the second case is that you made a wrong prediction, and then we should take into account the components which are wasted, and also the profit which we miss because we did not fully produce the product. Eventually that resulted in that the SEP method was actually profitable, and the neural network method was not profitable because the neural network method had a low precision, which resulted in that the saved component costs did not exceed the missed profit. To conclude, we can state some lessons learned was that the training with the single label was quite problematic. We actually then trained the models with false information because we used one single label for all individual workstations. And also that the process deviations introduced quite some problems for the model because the dataset was not steady state. To follow up, we want to further subdivide the classification label. So for instance, we can see up till which production cell it has produced before it went scrap, or which test information was assigned to it that it went scrap. Also, we can use some more additional inputs. For instance, we can take into account cost. So if a product is at the end of the line and it's maybe classified as scrap, we can make a cost model which takes into account the costs which are added further versus the missed profit. We can put this first in a live monitoring environment so we can see how the model works in practice based on the real life data. So this can already be used by engineers to see how it performs and help them in their root cause analysis. And we can also then test on a more steady state data set with less process deviations. So now Usman will tell you more about machine learning monitoring.
Hello and welcome to this talk on machine learning monitoring. So allow me to introduce myself. My name is Usman Zafar. I work as a machine learning engineer for Go Data Driven. A bit about my background. I have a bachelor's degree in physics from Imperial College London. I later, like many of you, went into the world of data. So I studied machine learning at a postgraduate level. I also specialized in computational neuroscience, where I was working on developing a model for insect neurons based on experimental recording of those insects and how their proteins changed in their brains. Despite it being very interesting, I feel like it's going to be more interesting for people in 30, 40 years' time. And so I had a desperation to do something that was more towards industry, so I could provide some impact in the real world. Aside from that, I live in Amsterdam with my girlfriend and 2 cats, and I'm also a cycling enthusiast, although my girlfriend would call it an obsession. She's probably correct. So the agenda for today, we're going to talk about monitoring. It may have a reputation of being the boring aspect of machine learning, but it's nonetheless important. We'll talk about why it's sometimes an afterthought. Also comparisons with software engineering and why that sometimes is not the best analogy. We'll go through some of the problems we have in monitoring. We'll break it down in terms of functional and operational and the components that make up this topic, and talk about some concepts such as data drift and concept and model drift. And finally, we'll talk about teams and technologies and how we can structure those properly to help us in this topic. So deploying machine learning models to production so that they're operating in a business, providing value, is undoubtedly a very difficult task for any team. And it's a huge milestone when that final deployment is done. And so it can feel like the end of the road. But it is actually, we're only halfway there, in the words of Bon Jovi. Because once we've shifted towards the post-deployment phase, it's now about how we manage this in production. If we think about ML Ops, which is a term that has really grown in popularity over the past few years, it really highlights the emphasis on the machinery around the model so that it can operate in a business. I think as data scientists and machine learning engineers, there's always a lot of focus on the model. I'd say we're very model-centric, so much so that there's even a data-centric AI movement that tries to shift some of the focus back towards the data and the other components around the model. If we think about the typical machine learning pipeline, so we have input data, some pre-processing, a model, some training, then deploying that somewhere as an endpoint in some infrastructure, and finally monitoring. I'd say at the very center at the model, that's where the interesting stuff is, right? That's the sexy part, the neural networks, the graph neural networks, all these fancy NLP models. And the further away we get from there, the interest seems to drop off. And that's an issue because each area needs a sufficient amount of focus in order for us to make machine learning models successful in production. So our roles, data scientists, machine learning engineers, they really came into prominence over the past 10 years. It's quite a new industry, but we're very fortunate that we've adopted a lot of things from the world of software. Who've been doing this for 50, 60 years. Effectively, the tools we use are the same, programming languages, so a lot of the concepts kind of cross over as well, how we structure our programs, unit tests, integration tests, the separation of environments, all those things we've borrowed from the world of software, and we can apply quite nicely here. But with monitoring, there's a slight difference. The fundamental nature of what we have is different. With kind of software, you have something that is explicitly programmed traditionally. And what we have, our kind of program is a parameterized model. And those parameters are determined by some optimization method. In the case of really complex neural networks, you can have millions of parameters determined by a series of calculations that we don't explicitly define. So it's those very parameters that determine the flow of our software. And therefore we have this inherent uncertainty around what goes in and what goes out. Of course, during training time, we have control over the data we put in, and therefore the data we get out. But then once we deploy this in the wild, and there's the real world data interacting with this, there's simply no way to gauge what's going to happen. Lots of models tend to take lots of different features, so that input space is really high dimensional. It's impossible to be able to understand what happens in every space in that really high dimensional space. And so, typically this is defined, some people would use the term software 1.0 and software 2.0. 1.0 is a traditional one, and then 2.0 is the kind of, this new parameterized way of doing things. And that has implications on monitoring, which is why sometimes we have to define our own frameworks and processes for dealing with these problems. And we can't simply just lift and shift from the world of software. So what types of problems do we have when monitoring is perhaps ignored or not implemented in the best way? Well, the first and probably the most common is changes in the distribution of your data. We live in a changing world, so it's impossible that the data you use at training time is going to be similar to what you have when it's live. Also skews between training data and live data, so this is when there's perhaps a significant shift. A good example of this is during the pandemic, all of a sudden facial recognition started to fail because we were all wearing masks. That's a real skew between what the facial recognition software was trained on. Outliers. Again, input data is really large. It's impossible to cover all the space that is spanned by our features. There's pipeline-related issues. Don't forget that whilst data we consume may be in a nice format, there's really complex ways that's input there, and there's issues that can occur there. And uncertainties around what value are we actually adding to the business from this model. So monitoring can be broken down into two separate, for the machine learning context, into two separate categories, operational and functional. Operational is quite similar to traditional software, where we're looking at the very systems and resources on which we're running our machine learning models. So latency, CPU and GPU usage, number of requests, failed requests, that kind of thing. And functional is about the performance of the models itself. So the data science and machine learning specific metrics. So operational is something which typically gets pushed onto DevOps teams because there's a lot of overlap with what they do. But I think there's also important lessons for us here too. An interesting example is around latency and how this can impact the predicted performance of our model. So even though it's an operational metric, it does have consequences for our use case too. The one example I want to give is, imagine we have a store where we sell lots of different items, and we have a system built in where we can dynamically change the price of those items based on what's happening live in those stores. Now, if we're to see that some products have low sales, therefore we may want to increase the discount on them, thereby increasing their sales. But the time it takes in which that data is processed and then sent back to the store is critical. If you think about the lunchtime period, where it's a really busy period, if you're taking in this input data and then your predictions are too late, then you're acting too late, and therefore you have issues. So functional can be broken down further into three separate components. Briefly, your input data, your model, and your predictions. For your input data, you can think about your source data. So there's probably several sources. Usually we have data in some kind of convenient data warehouse. That data warehouse itself is a result of a really complex ETL process, lots of different sources, lots of types of sources, streaming, traditional databases. If one of those is not updated, then you are using stale data in your pipeline. So the question to ask yourself is, do we actually have an overview of that? Are we using updated data sources? If a data source is not updated, do we know that? If not, then potentially there's going to be problems downstream from our own model. And we'd rather catch these problems early on, of course. Then there's the model itself. So in this example here, we can see that the data is exactly the same, but the decision boundary is changing. So this means that the predictive nature between our input and output is changing. The function that maps input to output no longer holds. This can also be gradual or sudden. For example, during the pandemic, there was no way that supermarket forecasting algorithms could have predicted the enormous growth of toilet paper usage. And predictions. So on the left-hand side, you can see we have three separate classes, green, orange, and blue, in relatively similar proportions, but maybe in the future that changes. Maybe one of your classes becomes irrelevant. This also changes then, other things relating to your input data and model, and something you want to be aware of. But also value. We mustn't forget that the performance of our model is not some accuracy measure. It's not about having 99% accuracy or an RMC of 0. Ultimately, our predictions are used downstream by some other business process. And the idea is there is some actual tangible value as a result, usually, ideally measured in money, a language everyone speaks. So an example use case I want to give about how this can go wrong is in an e-commerce setting. I want us to imagine that we have lots of stores in a region and we sell various items in those stores. And we want to produce a demand forecast so that we can determine how much of each item in each store we need to supply to make sure there's sufficient demand. So it's important to be aware here that we, as data scientists, are producing these predictions which are then passed on to business teams, and that there is actually a subsequent process that occurs from this. So you can see here there's all sorts of lorries which are being driven to various stores around this region. Now, one issue I noticed in a project which kind of broadly relates to this, although the specific use case has been obfuscated, so no client can be recognizable, is that from the data science perspective, their main focus was on the MAPE, the mean average percentage error. And so when they had two models with identical MAPE values, they were seen as the same. But actually, they can have very different financial implications. For example, if you underpredict on some items that are really cheap, it's very different to underpredicting on items that are very expensive. And that was missed. And this is a situation in which the wrong thing was being measured. And the ultimate aim of the team was to satisfy some statistical measure, but not the business value. Furthermore, if you can see here, these predictions are then used by business teams. But how are they used? Do the business teams even follow those? Prior to the implementation of a neural network architecture, these predictions were generated by moving averages. Now, how those business teams use these values, again, was not monitored, and therefore it's impossible to know whether they are even using these predictions. So this is another instance in which the kind of downstream usage was just ignored, and so that remained a black box. So an important concept in monitoring is data drift. We live in a naturally evolving world. Data changes, that's completely normal. But when we train our models, we have a static data set. Ideally, we want what to happen at training time to kind of match what happens at prediction time. But that's going to be quite hard when, the data set we have is just singular. And so naturally, data drifts over time. And that's something we want to monitor. It's usually gradual because the world generally changes in a gradual way, and it's something you want to catch early on so that you can retrain your models or redefine your features. So if it shifts in such a way that here on the right-hand side you can see there's no separation anymore, then you would have to redefine your features so there is such a separation. There's also concept drift. As I briefly mentioned before, your model can change over time. In the context of a recommender system, for example, maybe your recommendations are becoming slowly out of date as user preferences change. Or they can be sudden, as was the case, like I mentioned before, with the pandemic, where people suddenly had very high demand for specific products. Now, a slightly alternative view is that models should be robust enough to actually handle this drift. So in this example here, we can see that data is actually drifting away, but is defined in such a way that our decision boundary is robust enough to deal with such a thing. And actually, if a model is robust to a bit of drift, that's fine. And the most important metric we should monitor is user feedback. This should be built in directly to the systems. Ultimately, like I mentioned before, our models are used for some downstream purpose, and it's our performance on that purpose which matters the most. Here is another example of the robustness of models. You can see here that this model on the right, was trained to pick up blocks in real life, but it was trained on simulation data. Quite naturally, there is a big skew here between the training data and the prediction data. One is real life and one is a simulation. But the robustness of the model has allowed us to make it so that that's not an issue. So how can user feedback be implemented? A nice example of this is the autopilot feature that Tesla is working on. So here we have some stop signs. Stop signs are typically straightforward, you would imagine. It's just a red hexagon with the word stop on it. But it actually gets a bit more complicated than that. For example, they can be obfuscated by trees and other items. At the bottom here, we see that the stop is only valid for when you're turning left, not when you're turning right. A stop sign can also be upside down, can be held by someone, by a traffic warden. If they're holding it up, it's active. If they're holding it by the side, it's not active. And the autopilot system is designed in such a way that when unconfident predictions are made, then they are fed back into the system and then created as separate data sets so that you can generate useful data sets of your problematic areas. And this immediate feedback allows the overall model to become better. So over the projects I've worked on, I've noticed a couple of things. Structuring streams is really important when trying to solve this. Often teams are overloaded with data scientists, and there's a bit of a lack of cloud and engineering knowledge. And as a result, things like monitoring, which are perhaps a bit more abstract for a data scientist, tend to get ignored. And technologies. Mentioned at the very end, I think ultimately monitoring is not a technology problem, but a people problem. Quite often something goes wrong, and then the monitoring is then built to make sure it doesn't go wrong again, which means we have a very reactive mindset towards this, but it's not very proactive. I think by having a proactive mindset, whilst also structuring teams to be multidisciplinary and less reliant on external teams, it can make us more dynamic and to actually address these other parts of machine learning that are needed to make sure our models are productionized and that so they can be managed effectively. But I want to briefly mention Evidently. It's an open source framework to test and monitor machine learning models. Has a wide range of features and nice dashboarding features. One tiny part of functionality I want to mention is its ability to monitor numerical predictions and how they drift. So you can see here on the top left-hand side, we compare the training data set with the production data set and see what the distributions are like. On the bottom here, we look at the correlations between the output values we have versus the input features we have, broken down both by training data and production data. And on the right-hand side, we can see how this evolves throughout time. And they have a whole range of standard statistical tests that are included out of the box, which makes it nice and easy to work with. And I also briefly want to mention SageMaker and Vertex AI, the respective ML ops frameworks for AWS and GCP. They also have out-of-the-box functionality for these things, somewhat limited compared to Evidently. But if you're already using those services, then it's quite easy to add on and requires not much extra work. So there's less complexity to do this. So to summarize, we spoke a little bit about monitoring and why it's important, why it's also often an afterthought. We broke down the differences between functional and operational monitoring, about why software is maybe not the best analogy and why that is problematic for us. The concept of data and model drift, but also user feedback. We spoke also about the downstream value of our models. It's important to remember that there is some real-world impact to this. And finally, we briefly touched on teams and technologies and how we can make sure we address those properly so that we can address monitoring and the wider kind of ML ops principles better. Thank you.